All right. So, whenever that was, Wednesday, we talked about work and went through and got some formulas on that. Worked a few problems. We'll work a few more today. So I want to take some time and I want to talk about kinetic energy. When you hear words like this, I want you to think about them. And I just want you to think about them for a minute. Zip, zoom, hover, race. So if I'm describing an object and I use the words zip, zoom, hover, race, what do the bulk of those words make you think about? Or movement, moving. Are there any of them that don't make you think about moving, or is there one that doesn't fit? Hover. So what does it mean to hover? Float above, but I'm not moving, right? I'm just kind of levitating. Right. So you got to think about the difference. If I say zip, zoom, race, I'm talking about kinetic energy. And these three things, I'm talking about motion. If I'm hovering, am I sitting on the ground? No, that would not be hovering. Can I be just a little bit above the ground and hover? Yeah, there's hovercrafts that just like skim the floor, and then there are hovercrafts that like you can take a drone and make it hover, and then you can call it a hovercraft, really. If you're really good at the controls, you can do that. It's kind of hard. This one really should make you think about potential energy. Can I be hovering and have both potential energy and kinetic energy? Yeah, because what keeps me hovering? Air and air being pushed down, you're right. If I think about an actual drone that's hovering, what part is still in motion when a drone is hovering? Do you know? Yeah, the propellers. So I can take one object and I can look at it in a bunch of different ways. We're going to start by looking at kinetic energy. And I'm going to say that KE depends on two things. And they are both think of the right way to say this. They're both properties of the object. So it doesn't depend on anything else. It just depends on the object you're identifying, the object you're looking at. And those two things are the mass of the object and the velocity of the object. So everything kinetic energy depends on has to do with the object you're studying. When we look at potential energy later, we'll see that's not true. Why don't you take a minute and get your formula card out. So if I take the properties of that object and I put them into a formula that deals with kinetic energy, I get something that looks like this. Ke equals 1/2 mv squared. Or kinetic energy equals 1/2 the mass times the velocity squared. And don't forget to square your velocity. Or if you're solving for it, find the square root of it. Those are some of the things that people mess up with. When we use this formula, we treat the object as a particle. Doesn't matter how big or how little it is. This 1/2 mv squared was originally figured out using atoms, and that's why we say we treat the object as a particle. The SI unit of measure for any form of energy is a joule, and sometimes we use kilojoules. If I have 1,000 joules, then I have 1 kilojoule. So if you have something really large, you might have to convert it to kilojoules. Or if I give you kilojoules, if you want to use it in the problem, you have to convert it back to joules. The same way, like any of these, this should be, and we probably should write this down, this should be meters per second. So it's one of those kind of problems where if you're given kilometers per hour, the first thing you need to do is convert to meters per second before you plug it into the formula. So watch for that. All right, let's put this problem in your notes and then just stop. Yep, A and B. We'll do them both. Then you'll have an example of both for your notes. When you got them, just drop your pencil so I know you don't really have to drop it, but lay your pencil down and then I'll know you're ready. We good? I'm not sure. You good, Lindy? Yeah. Okay. All right, so let's look at this. Too many papers. Let's look at part A first. 7-kilogram bowling ball moves at 3 meters per second. How much kinetic energy does the ball have? That's really nice and straightforward. So it's asking me about kinetic energy. So I know I'm going to use 1/2 mv squared. Then I'm going to come down here, and it's asking me KE, so I'll put my question mark, fill in my mass, and my velocity is 3.00 meters per second, and my mass was 7.00 kilograms. That's nice and straightforward. I'm just going to have to plug it in. So KE equals 1/2 7.00 kilograms times 3.00 meters per second squared. Plug it in and see what KE equals for me. What'd you get, Kira? 31.5 what? Joules, or kilograms times meters per second.
Do we have to convert it to, like, does it need to be in kilograms or grams?
It needs to be in kilograms. So if I gave it to you in grams, like I did in the next part, we'll have to convert it. So let's look at B. I keep turning my paper over. So in B, how fast must a 2.45 gram ping pong ball move to have the same kinetic energy? So this time I'm using the same KE from above. So I'm going to carry it down. And my mass, I gave it to you in grams, so I have to convert. That would be 0.00245 kilograms. And I have to find my velocity. So I end up with an equation when I plug things in that looks like 31.5 joules equals 1/2 0.00245 kilograms times V squared. Now I'm going to put that over on the other paper so it's bigger so we can see it. 31.5 joules equals 1/2. So the first thing I want to do, and I'm going to work through this because sometimes we have difficulties with this, I want to get V squared by itself. To get V squared by itself, I'm going to divide through by 1/2 times 0.00245 kilograms on both sides of my equation. So I'll carry that down. 31.5 joules divided by 0.5 times 0.00245 kilograms equals V squared. Does that make sense to everybody why I did that? Yeah? No questions? Now plug that into your calculator. It's kind of a big number, I bet. Let's see. 25,714? Is that right? 25,714.3 joules. This should be. What? Yes, it's under the 31.5.
I thought we just, that's
Ah, no, 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 no. No, no, no. I divided already. I don't know why I carried that down. So that equals V squared. Now what do I need to do? Square root it. Yep. So I have, what do I have? 160.36 equals V. How many sig figs am I allowed to have? 3, so 1.60 times 10 to the second joules equals V. Now, let's take a second, because I know we're not going to be able to get all the way through the potential energy stuff that I want to, so I think what we're going to do, pull out your problems. I had you guys go to what, number 4 or 5?
7.
Oh, good. Okay. I was thinking we weren't that far. All right, so then we can go a little bit farther. And then we'll break into groups, and you should have enough time to get done what I need you to get done today. So we're only going to talk about today one kind of potential energy. And then we'll save the other one for Monday, and then we'll go into lab. So one thing we need to remember right now, as we move through all these things, if we have a perfect system, then KE can be set equal to PE. If I have a perfect system. If I disregard friction, air resistance, and all that other stuff. I also can say that work can be set total, or set equal to energy total. Things we have to remember when we do problems. Again, those are both in a perfect system. And we'll use them later. If I ask you what potential energy is, can you tell me, like in 2 words, what it is? Good. Energy stored, stored energy, however you choose to say it. It is stored energy. Another way to think about it that's a little longer and helps you explain things better later is that an object that has the potential to move bless you, because of its position, and this is the important part, this is the part that always gets left off, like when you learn it back at the junior high, with respect to some other location. This some other location, it can be lots of different things, but it's 0 level, and we'll talk more about 0 level, but it becomes really important in these problems. We have to be, when we're dealing with potential energy, we have to be comparing it to something, or it doesn't mean anything. It's useless information. PE is different from KE. Flip back after you write that in your notes and see, what did we say that KE depends on? Properties of what? What did we say KE depends on? Yeah, the mass and velocity of the object, the properties of the object. PE does not depend on properties of the object. Alone. It does depend on perhaps the mass or some individual property, but not just the object's properties. It also depends on interaction with the defined environment. So there's something outside of that object itself that we have to pay attention to. That's what it's saying. There are two types of PE. We're only going to learn one today. Type 1 is called gravitational potential energy. And if you have to define this, or if you're asked about it, it is the energy associated with an object due to its position relative to a gravitational source. So in other words, you have this because you're somewhere that has gravity. Energy associated with an object due to its position relative to a gravitational force. That's why it's called gravitational potential energy, because we have to take gravity into consideration. So if you're asked for gravitational potential energy, would it be the same here as it would be on Mars, as it would be on the moon? No, because we have all different values for acceleration due to gravity. But if I take this definition and I make it a formula, which I can do, I can say that PEG, or PE gravitational, is equal to mass times gravity, whatever that value is, times height, or PEG equals mgh. Looky there. What's mg? What equals mg? Blank equals mg. Wait, so it's like WH, really. And you really have to think about these. You really have to think about the position of the object in reference to wherever your zero level is. So, turn around and look at the cabinets back there. You see how there's like, I could say there's an upper level, and I could potentially put something up there, and then I could compare it to the lab counter, or I could compare it to the floor. When I do that, I have two different 0 points. Like if I say I'm going to release a ball and it's going to land on the lab counter, that's one height. It could be my base level if I define it as 0 point. Or I could say I'm going to drop that ball all the way to the floor. Then the floor would be my 0 level. Does that make sense? So we can label those kind of things, like maybe we should put that drawing in there so you've got it for later. So this would be, we'll make that point 1, point 2, point 3. Let's say I have a ball on the edge of the top cabinet. And I say it's going to fall, and it's going to stop. Then my 0 level would just be 0.2. I wouldn't be worried about any of this stuff down here. So when I find my height in this particular diagram, it would be equal to what? 2 minus 1. Or really, I guess, yeah, you could do it either way. Now what if I take that ball, I'm going to make this a little smaller so I don't run out of room. And I let it fall all the way to the floor. So I've got a 1, a 2, and a 3 still. And my ball's going to start up here. It's going to land here, roll, and land at the bottom. So this would be now my 0 level. So when you get these problems, you have to ask yourself, oh, where am I landing and what's my 0 level? Here my height would be the 3 minus 1, or h total in that diagram. Up here, from where the ball starts, that's not really total height. It has potential to go further. When I look at this, if this is my floor, and this is my cabinet top, or countertop, whatever you want to call it, when this ball lands here, and it stops, is there still potential energy? Yeah, it could go further down, right? There's still some height. Do I have any potential energy left here? No, I should be at rest if I have the ball made of the right material. So that gets really important, paying attention to 0 level. And that's where I want to stop. I want you guys to break into groups, and I want you to get done through number, let's do through number 11 today. Yeah, through number 11. We should be able to get there. If you get that far, let me check them, and then I might give you another one to do.